Welcome to this fascinating journey into the world of reinforcement learning. This field of study is a branch of artificial intelligence that focuses on how an agent should take actions in an environment to maximize some notion of cumulative reward. It's like teaching a dog new tricks. You reward the dog with a treat when it does something right, and over time, the dog learns to repeat the rewarded behavior. One classic use case of reinforcement learning is Google's search algorithm. When you type a query into Google, the search engine displays a list of results. Each time you click on a link, Google takes it as a positive reinforcement, learning that the link was a good match for your query. Over time, by learning from millions of such interactions, Google's algorithm has become incredibly good at predicting what links will be useful for a given search query. But reinforcement learning isn't just about search engines. It's being used in a wide range of applications, from self-driving cars to recommendation systems, and from game playing to sequence prediction. It's the engine behind some of the most exciting advancements in AI, including DeepMind's AlphaGo, which famously defeated the world champion Go player. Reinforcement learning is built on the idea of the agent-environment interaction. The agent, which can be a robot, a computer program, or any other automated system, interacts with its environment by taking actions, receiving feedback from the environment in the form of rewards or punishments, and learning from this feedback to improve its future actions. This learning process is typically modeled as a Markov decision process, a mathematical framework that provides a formal way of describing an environment and how an agent can interact with it. It's a powerful tool that allows us to mathematically analyze and solve complex reinforcement learning problems. So whether you're interested in mastering the latest AI technologies or just curious about how machines can learn from their own experiences, reinforcement learning has something to offer you. It's a fascinating field that's pushing the boundaries of what machines can do. That was a brief insight into the world of reinforcement learning. Now, it's time to delve deeper and explore Q-learning. Q-learning is a model-free reinforcement learning algorithm, meaning it doesn't require a model of the environment to make decisions. It's an off-policy learner, which means it learns the value of the optimal policy irrespective of the action taken. Imagine you're playing a game of chess. Each move you make is like taking an action in a particular state of the game. The aim is to checkmate the opponent's king, which can be seen as the ultimate reward. In Q-learning, you'd learn by playing the game over and over, each time updating your understanding of the best moves to make in each state based on the rewards you receive. To be a bit more technical, Q-learning involves learning a policy, a set of rules that decides the agent's actions. This policy is called a Q function and is used to approximate the return or the total reward from each action in each state. The beauty of Q-learning is that it can compare the expected utility of the available actions without requiring a model of the environment. It uses a table to store the Q values for all possible combinations of states and actions. Over time, as the agent explores the environment, these Q values are updated using the Bellman equation, which essentially allows the agent to estimate the expected future reward from each action in each state. Q-learning differs from other machine learning techniques in that it's an active learner. It's not just passively observing data and learning patterns. Instead, it's interacting with its environment, making decisions, and learning from the consequences. And what's more, Q-learning can be combined with other techniques to form more complex algorithms. For instance, deep Q-learning combines Q-learning with deep neural networks, allowing the algorithm to handle high-dimensional state spaces more effectively. And that's Q-learning in a nutshell. Next, we'll get our hands dirty with deep Q-learning. This approach is a fascinating blend of traditional Q-learning with the power of deep neural networks. To put it simply, deep Q-learning uses a neural network to approximate the Q-value function, and this network is referred to as a Q-network. The main advantage of deep Q-learning is its ability to handle high-dimensional state spaces, which is a common occurrence in many real-world problems. This is where traditional Q-learning would struggle, but deep Q-learning shines. Now let's talk about implementing deep Q-learning. The first step involves initializing the Q-network. This network will take the state as input and output the Q value for each possible action. Next, we define the experience replay. This is a memory buffer that stores the agent's experiences throughout its exploration of the environment. This replay buffer is crucial as it allows the network to learn from past experiences, thereby improving the efficiency of the learning process. Now let's imagine our agent is playing a video game. It uses the Q network to choose an action based on the current state. It then performs the action, receives a reward, and lands in a new state. This sequence, state, action, reward, new state, is known as an experience, and it's stored in our replay buffer. Periodically, we sample a batch of experiences from the replay buffer and use these to train our Q network. Here, our aim is to minimize the difference between the Q network's prediction and the actual Q value obtained from the game. This process is repeated until the network's predictions are as close as possible to the actual Q values. The beauty of deep Q learning lies in its broad applicability. It has been successfully used in a variety of tasks, from playing video games to optimizing industrial processes, making it a powerful tool in the arsenal of reinforcement learning techniques. That was a quick run-through of deep Q learning. Stay tuned as we dive deeper into the world of reinforcement learning in the next segment. Let's now steer towards deep convolutional Q learning. This fascinating technique combines the power of deep learning with the practicality of Q learning, enabling machines to learn from high-dimensional raw inputs. Take image recognition, for instance. In traditional Q learning, we would need to manually extract features from each image, a tedious and time-consuming process. But with deep convolutional Q learning, we can let the model do this heavy lifting for us. It uses convolutional neural networks, or CNNs, to automatically extract and learn features from raw images. Here's how it works. The CNN takes in the raw pixels of an image and applies a series of filters to create a condensed representation, known as a feature map. This map is then used as input for the Q-learning algorithm. The result? A highly efficient learning process capable of handling complex tasks. The benefits of deep convolutional Q-learning are manifold. It's more efficient as it automates the feature extraction process. It's also more versatile as it can handle a wide range of tasks, from gameplaying to autonomous driving. And it's more accurate as it can learn from raw, high-resolution inputs. But how do we implement deep convolutional Q learning? It's a multi-step process. First, we feed the raw inputs into the CNN, which generates the feature map. Then we use this map as the state representation in the Q-learning algorithm. We also use a technique known as experience replay, where we store and randomly sample past experiences to break the correlation between sequential states. This helps to stabilize and improve the learning process. And just like that, we've built a model that can learn from raw inputs, making complex decisions based on its own experiences. This is the power of deep convolutional Q learning, a testament to the incredible potential of AI. So the next time you see an AI effortlessly identifying objects and images, remember, there's a good chance it's using deep convolutional Q learning to make that magic happen. That was an overview of deep convolutional Q learning. Finally, we'll touch upon the 3 A's in A3C. A 3C stands for asynchronous advantage actor critic, a mouthful indeed, but an algorithm that's had a significant impact on the field of reinforcement learning. It's a method that combines a number of techniques to create a powerful, scalable solution for complex problems. Firstly, let's discuss the actor. In the context of reinforcement learning, an actor is an agent that takes actions in an environment to achieve a goal. Think of it as a player in a multiplayer online game, making decisions based on the current state of the game, with the aim of maximizing its score. Next, we have asynchronous. In traditional reinforcement learning algorithms, learning is a sequential process. But in A3C, multiple instances of the agent interact with multiple instances of the environment at the same time. This asynchronous approach speeds up learning and helps the agent to explore a wider range of possibilities. Picture our online game player, but now there are many of them, each playing their own game independently and learning from their collective experiences. Lastly, the advantage component of A3C helps us to quantify how much better an action is compared to the average action at that state. It essentially helps the agent to understand which actions are advantageous and should be taken more often. Going back to our game analogy, it helps the player understand which moves are likely to increase their score based on past experiences. By combining the actor, asynchronous nature, and advantage function, A3C provides a robust and efficient framework for training artificial intelligence to tackle complex tasks, whether it's mastering a game, navigating a robot, or optimizing a system. That wraps up our journey into reinforcement learning. we've covered a lot of ground from the basics of Q learning to the advanced concepts of A3C. I hope you found this journey as fascinating as I have. Stay tuned for our next video where we'll delve into the exciting world of large language models. We'll discuss what they are, who invented them, and how they generate text.